For today's lesson, we are going to finish section 8.2 from our text. Namely, we will be proving another statement about countable sets, and then we will move towards Cantor's theorem. So, as a recap from our last lesson, at the end, we proved that the union of countably many countable sets is countable. Our first result today will use this theorem to then prove that if we have a countable set A, and we consider all the possible finite sequences within that set A, that union is going to be countable. And so theorem A22 will play an important role. I should also mention that the proof that I will be doing for this result is going to be different than that in the textbook. The textbook does it by induction. We will proceed without induction. Following our proof of that theorem, we're going to move towards uncountable sets. As of now, our treatment of infinite sets has been specifically in the numerable case, so recall, countable means numerable or finite. And so now we will actually proceed towards the situation of uncountable sets. And so specifically, we will prove Cantor's theorem from 1892, which states that if we have any set A, then A is not equinumerous to the power set of A. And we will conclude today's lesson with the famous diagonalization argument due to Cantor, which proves that the real numbers are uncountable. And then one question that we want to keep in mind going forward, and this is going to be addressed in the next lesson, is if the real numbers are uncountable, is it the case that the real numbers are equinumerous to the power set of the natural numbers, or is it not? Since we will know from Cantor's theorem that the natural numbers are not equinumerous to the power set of the naturals. So the power set of the naturals is uncountable by Cantor's theorem, and we are going to prove that the real numbers are uncountable. So are the real number? How do the cardinalities of the real numbers and the power set of the natural numbers compare, since both of these are uncountable sets? And so these are questions we will focus on in our next lesson. So let us go ahead and get started. Our first definition is going to be that of a finite sequence. We are used to sequences from our previous math courses, but now we are going to redefine it, and it's going to depend on a function. And so let's see how this definition ties in with our preconceived notions of what a sequence is. So we're going to take A to be any set, and we're going to define a function f from I sub n to A, where I sub n, as a reminder, is the set of positive integers I, such that I is less than or equal to n. Well, we are going to call the function f from I sub n to A, where n is a natural number, a finite sequence of elements of A, and n is called the length of the sequence. So how does this tie in with what we know of sequences? Well, let us look at the Fibonacci sequence. So we've studied this already when we looked at section 6.4. The only difference between the definition I have here for the Fibonacci sequence and what we saw previously is where they start. When we considered the Fibonacci sequence earlier in the course, we started at f sub 0. And so we defined f sub 0 to be equal to 1, f sub 2 to be equal to 1, f sub 1 to be equal to 1, and then we define it recursively. The only difference now is we're taking f1 to be equal to 1, f2 to be equal to 1, and now f3 is equal to 2, f4 is equal to 3, so on and so forth. And so we still get back the Fibonacci sequence, and in more generality we have capital F sub m is equal to f sub m minus 1 plus f sub m minus 2 for all m greater than or equal to 3. So we are used to interpreting this sequence of numbers, say 1, 1, 2, 3, 5, as a sequence. This is a finite sequence from our previous notion of sequences. The difference now is that we want to define finite sequences not in this way of having a finite list of numbers, but rather via a function. And so we have g, and I'm going to label this g sub 5. And here we have a function going from I sub 5 to the integers. And so the integers in this case is our set A. defined by g sub 5 of j goes to capital F sub j. And so now we see that if we were to look at the list of numbers, g sub 5 of 1, g sub 5 of 2, g sub 5 of 3, g sub 5 of 4, and finally g sub 5 of 5, that this here is going to be equal to f1, f2, f3, f4, f5. But that is now 1, 1, 2, 3, 5. And so we do get back the finite sequence that we are accustomed to. And so we just slightly abstracted things in this manner, but we still have our list of numbers corresponding to that finite sequence. And in more generality, we have g sub n, where this is going from I sub n to the integers, defined by g sub n of j goes to the j Fibonacci number. And so g sub n is what we will call is a finite sequence of integers corresponding to the sequence of the first n Fibonacci numbers. And so that's how this ties in with our previous notion of what it means to be a finite sequence. Okay, so now that we've mentioned that, let us also recall that g sub n is a function, and therefore it is a relation. And so in particular we have that g sub n. If we think about it from that point of view, we have g sub n is really the set of elements j comma g sub n of j, where now j ranges over all the integers. But this here is a subset of I sub n Cartesian product the integers. And so what we want to do now is consider all the possible sequences of a set A that are finite. And is that countable if we were to look at the whole collection? And so that's the next theorem. So theorem 824, which tells us that if A is a countable set, then the set of all finite sequences of elements of A is also countable. So the proof that we are about to do is going to be slightly different than that done in the textbook. Our argument will start in the same manner, but the method of proof will be different. So for example, for the scratch work, we're going to let S sub n be the set of all finite sequences of length n in A. In other words, S sub n, we can think about it symbolically as the set of f's such that f is a function going from I sub n to A. And so that's the definition of what it means to be a finite sequence of length n. And so we're looking at the set of all finite sequences of a given length n. In the textbook, the proof starts off by showing that S sub n is countable via induction. Our proof is going to be slightly different in that we're going to rely on the following claim, which we have not proven yet, but I will prove after the theorem of 824. And so what this claim says is the following. If A is a countable set, then the Cartesian product of A with itself, and let me write this, then for each positive integer n, A sub n, where now this is the Cartesian product of A with itself, n times is countable. So the proof of this is via induction, and the inductive step will just rely on theorem 821. So we're going to prove this in just a bit. So let's go ahead and assume the claim. And let h be a function from S sub n to the Cartesian product of A with itself n times, defined by h, and now the input is a function, and the output is going to be the following. We know that every element of S sub n is a function of the form going from I sub n to A. But I sub n is all the positive integers, 1, 2, 3, all the way until we get to n. And so we're going to take the ordered pair that goes from h, for h of f is going to be f of 1, comma, f of 2, comma, f of 3. And so we're just going to have that finite sequence all the way until we get to the nth term. And this is going to be, of course, an element in the Cartesian product of A with itself n times, since by definition of f, the outputs are all in A. So all these elements are in A, and now we have an element of A sub n. This is going to be a one-to-one function, and of course we have to prove this. But I will leave the proof of this to our formal proof. And so this is a one-to-one function. Next, we are going to use theorem 815. If we use the claim, we know that a to the n is countable. And since a to the n is countable, we have that theorem 815 tells us that a countable set is equivalent to the existence of a one-to-one function going from that set to the positive integers. So by theorem 815, there is a function going from a to the n to the positive integers that is 1 to 1. And now we have the theorem from chapter 5 that tells us that then the composition of L with h, which now goes from S sub n to the positive integers, is 1 to 1. And now another application of theorem 815 implies that S sub n is countable. And now we have that S sub n is countable. But now in this situation, the n was in fact an arbitrary positive integer, so we have that S sub n is going to be countable for every positive integer n. And now we apply theorem 822. And so now the set that we want is the set of all the S sub n's where we have that we take this union. But this here is going to be countable by theorem 822. Since now we are taking a union over all the natural numbers, but so we're indexing by the natural numbers. So we really do have a countable family of sets. S sub n, and it's a natural number. So just to write this in the notation of family of sets, this here is a collection of countably many sets. Each of the S sub n's is countable, and therefore the union of f, which is equal to this, which is then by in turn equal to the set of all finite sequences of elements of A. Now this has to be countable by theorem 822. And so that's the scratch work for theorem 824. So what I am going to do now is prove the lemma that it corresponds to the claim. And once we prove the claim, we are going to prove theorem 824. So let us begin with the proof of the lemma. we have A as a countable set, then A to the n, which is defined as the Cartesian product of A with itself n times, is countable for every positive integer n. So for the proof, we're going to start off for each positive integer n, we're going to let S of n be the statement. If A is countable, then A to the n is countable. Well, if we want to do this by induction, so we proceed by induction on n. For the base case, we observe that S of 1 is true since A to the 1 is equal to the A, which is countable by assumption. So suppose S of n were true, for some n. So next, let A be a countable set. And let B equal A to the n. By the induction hypothesis, B is countable and thus A to the n plus 1, which is equal to A Cartesian product B, is countable by theorem A to 1. And we are done. And so here we use theorem A to 1, which tells us that the Cartesian product of two sets is countable. And now we are ready to prove theorem A to 4 rigorously. So let's go ahead and do that. So here's the start of theorem A to 4. For n a natural number, we're going to let S of n denote the set of all finite sequences of elements of A which have length n. In other words, S of n is equal to the set of functions f such that f goes from I sub n to A, since that is the definition of what it means to be a finite sequence of elements of A having length n. So note that S sub 0 is equal to the set containing the empty set, since I sub 0 is equal to the empty set, and the only function f from the empty set to A is the empty set. And so we have S of 0, and so the S of 0 is going to be finite, namely countable. So we got that. So for any positive integer, define h going from S of n to the Cartesian product of A with itself n times by h of f is equal to f of 1, f of 2, so on and so forth. So now we're going to claim that this is a one-to-one function. So we claim that h is one-to-one. So suppose h of f is equal to h of g. This is equivalent to f of j equals g of j for each j in I sub n. To recall, since f and g are functions in S sub n, we have that their domains is I sub n. And so we got this equality for every j in In. Since f and g are they both have the same domains, namely I sub n, and the same set of outputs, a, and fj equals to g of j for each j in In, we conclude that f is in fact equal to g. Since two functions are equal, if and only if they have the same inputs, the same set of outputs, and are equal, and their outputs are equal for every element in their respective domains. And so we do get back equality of f and g. Thus, h is 1 to 1. By the lemma, a to the n is countable. Now we use Theorem 815, and so by Theorem 815, there is a 1-to-1 function, L, going from Cartesian product of A with itself n times to the positive integers. Therefore, the composition of L with H, which is a function going from S sub n to the positive integers, is 1 to 1 by Theorem 5 to 5. So this is the theorem that tells us that if we have a composition of 1-to-1 functions, then their composition is also 1 to 1. And by Theorem 815 once more, we have that S of n is countable. But now, n was chosen to be an arbitrary positive integer. Since n in the positive integers was arbitrary, we have that S of n is countable for each n, for each positive integer n. Now, here is a moment of possible confusion. In the past, this has not been a valid statement to conclude. If we have a statement of positive integers, we use induction to prove it, as the book does in this case. Now, what allows us to bypass this in our situation is that the lemma that we proved requires induction, and now we know that for every positive integer n, if a is countable, then the Cartesian product of a with itself is countable. So when we come to our proof, we are using that for some positive integer n, we know that a to the n is countable. And then we showed by this function h that S sub n is countable. But now that n is a fixed positive integer. And since we have already proven that a to the n is countable for every natural number, for every positive integer n, we now get that S of n also is countable for every positive integer n. But the key thing I want to emphasize is we are not using induction, but we really are, because we have already used the induction necessary in the lemma. And so it is really the lemma that is masking our ability to not require induction for this specific proof. Whereas in the textbook, they approach it directly without the lemma, and so they do induction. Now let us continue. We have now that S of n is countable for every positive integer n, but we also showed that S sub 0 is equal to the set containing the empty set, so that's countable. And so now we're going to go ahead and let us consider a family of sets. So next, let F be the family of sets S of n, where n is a natural number. In particular, F is a family of sets, is a family of countably many countable sets. By Theorem 822, we have that capital S, which is equal to the union of the family of sets, which is equal to the union as we range over all the natural numbers of the S of n's, is countable. Consequently, S is the set of all finite sequences of elements of A, and it is countable. And that finishes the proof. Now we are done. Because we're taking the union of all the finite sequences of length n. By taking the union over all the natural numbers n, we get back the set of all the finite sequences of elements of A. And that's exactly what we wanted to prove was countable. And so that finishes the proof of Theorem 824. So next up, we're going to prove Cantor's famous theorem. Let A be any set, then A is not equinumerous to the power set of A. Now, the proof of this result is actually not lengthy. It's quite fast. So now we're going to transition away. So with that last result, we are ready to move towards uncountable sets. And the first proof we're going to do is Cantor's famous theorem. Let A be any set, then A is not equinumerous to the power set of A. Before we even get into the proof, I want us just to go back to the timeline. Cantor proved his theorem in 1892. Now, the proof that we are about to do, which is Cantor's own, is very short. But that does not mean that it was something that Cantor came up with on the spot. This is the aspect of mathematics that I want you all to be mindful of as you go past this course. There will be theorems that you will see that are short, very clever, and that does, but them being short and clever does not mean that they were easy to come by. In the case of Cantor's theorem, we're looking at a statement that Cantor sought to prove for almost 20 years. If we go back to the timeline from our last lesson, we have that in 1872, 20 years before he proved his theorem, was when Cantor first introduced sets, along with the notation for union, intersection, set difference. A year after introducing sets, he was already thinking about questions of equinumerosity, namely his letter to Dedekind that asked him whether the real numbers were equinumerous to the natural numbers. Fast forward to 1877. He proved that the real numbers were equinumerous to Rn. His theorem, we know from his writings, had been conjectured by Cantor as early as 1873, that if A were any set, then A is never going to be equinumerous to the power set of A. And so for 19 years, he sought to prove this statement and failed. And finally, when he was able to prove it, he went back and reproved that the real numbers were uncountable through what we know today as Cantor's diagonalization argument, which far improved upon the complicated proof from 1874, which showed the uncountability of the real numbers. And so what we are going to do now is prove Cantor's theorem, and then transition to proving the real numbers being uncountable, but not the 1874 proof, but the proof that he did in 1892, following his showing that for any set A, then A is not equinumerous to the power set of A. And this is something that oftentimes happens in mathematics. Mathematicians work on questions to prove them, do not succeed. But then when they finally succeed, the proof may have been short, but that does not mean that it was an immediate but that does not mean that it was easy to come by. And I want you to reflect on the proofs you have done for this course. There are statements that you have proven that the final proof was short, but it being short does not convey the amount of time that you spent working on it. And keep that in mind as you read proofs in the future in mathematics. And if you go through the history time and time again, you'll see that the time spent trying to prove it was actually longer than what the length of the argument seems to convey. So let's go ahead and prove Cantor's theorem. So the start of the proof goes via contradiction. So we're supposing A is any set, and we're going to go by contradiction and suppose that A is equinumerous to the power set of A. Well, if A is equinumerous to the power set of A, then we have a bijective function f from A to the power set of A. And now comes the clever aspect of the proof, which 10 years later would motivate Bertrand Russell to develop his famed Russell's paradox. And so what we are going to do is define the following set. So let X be equal to that set of elements in A such that A is not in f of A. Now keep in mind, f is a function from A to the power set of A. So f of A is an element of the power set of A, and so this is going to be a subset of A. And so the way that this is defined is those A's and A's such that A is not an element of the set determined by f of A. And so X is a subset of elements of A, which is an element of the power set of A. And so we got this set. And now comes the clever aspect. Once we define this set, we know the function is bijective, so it is onto. So that means that there is an element that maps to X. Since f is onto, there is a B in A such that f of B is equal to X. Now we have two possibilities. And so the two possibilities are B is an X or B is not an X. And so I want you to think back to Russell's paradox, because we had something very similar, the set of all sets that do not contain themselves. And we did an argument where we considered where the set was a subset of itself and the case where it was not, both leading to a contradiction. Similarly here, we're going to assume both of these and show that we have a contradiction in both cases, ultimately contradicting that A is equinumerous to the power set of A. So case 1, so we show that both of these cases are impossible. And so case 1, suppose that b were an x. Well, if b is an x, that means that b is an element of this. But if b is an element, that means that b cannot be an element of f of b. But what is f of b? F of b is equal to x. Since that is what we took x to be, using the fact that f is onto. And so now we have b is an x, and b is not an x, which is a contradiction. And similarly, we look at case 2. Suppose b is not an x. Well, if we go back to the definition of what is x, if b is not in this set, that means that b is an element of f of b. And we now have b is not an x and b is an x. Once again, a contradiction. But now we have a contradiction of the fact that f is onto. So both of these cases contradict the fact that f is onto, and therefore it is the case that a is not equinumerous to the power set of a. And we are done. We have shown that a is not equinumerous to the power set of a, and as a consequence, we get what the textbook calls Cantor's theorem, which is the power set of the positive integers is uncountable. And so now we get that for free from our theorem, from Cantor's actual theorem. Now, what I want you all to do is to go through the proof that the book does for this statement as it introduces Cantor's diagonal argument. In the context of the power set of the positive integers, we are still going to see the same argument, but in the context of proving that the real numbers are uncountable. And so that's our next goal. So let us go ahead and prove that the real numbers are uncountable via Cantor's diagonalization argument. So here's the idea. So we're going to do the scratch work and then we'll formally prove this. So we know from homework that the real numbers are equinumerous to the interval 0, 1. And so now we're going to do contradiction. So we're going to suppose that R is countable. If R is countable, then since R is equinumerous to 0, 1, we have that 0, 1 is equinumerous to the positive integers. Then there is a bijective function f going from the positive integers to 0, 1. Then, if we take f of the positive integers, this is equal to 0, 1 since f is a bijection. So this tells us that we can list all the real numbers. In the interval 0, 1. So in other words, if I were to have f of 1 here, and then have f of 2, f of 3, f of 4, f of 5, and then continue on this way, counting by all the positive integers, 1, 2, 3, 4, ad infinitum, we will have every real number between 0 and 1 appearing exactly once in this list, since the function f is bijective. So now, let us go ahead and say that f of 1 is equal to the decimal expansion, 0, and then we're going to write the first digit. So in the 10th digit, we have a1, 1, a1, 2, a1, 3, so on and so forth. Now keep in mind, this notation is not multiplication. It's the digits in the decimal expansion, base 10. And so we have the 10th digit, the 100th, thousandths, so on and so forth. So we end up getting the following. So here's our list, and now what we are going to do is look at the diagonal entries. And we're going to define the following. So we're going to let, let's go ahead and call it x sub n, n. And this is going to be the following number. This is going to be equal to a, n, n plus 1 if a, n, n is less than or equal to 8. So again, these are all digits. So the digits are between 0 and 9. And it's going to be equal to 1 if a sub n, n is equal to 9. And so we got this x sub x n, n. Now, let x be 0 point, and then the first decimal entry of x is going to be x1, 1. Then the next one will be x2, 2, x3, 3, so on and so forth. And so we have its decimal expansion. Now x is going to be between 0 and 1. So note x is in the interval 0, 1. And since the function f that we have is bijective, we end up getting that there is some natural number. Let's go ahead and call it m. And I meant positive integer m, such that f of x is equal, f of m is equal to x. And so we have that x appears in our list. But why is that a problem? Pause the video and think about what's happening with this definition. Because now f of m means that we will have that number appearing in our list. But notice how x is defined. So pause the video and think about why this is a problem. Well, the problem lies that f of m, in the way that we wrote our list, is going to occur in some it's going to be some expansion of the form m, 1, m, 2, and then we just continue through all the digits until we get to a, m, m, and then we continue. Now, this is going to be equal to 0 point x1, 1, x2, 2, and then we just continue until we get to x, m, m, and then we continue. But these are both equal decimal expansions, which tells us that a, m, m is equal to x, m, m. And so we are getting that we must have equality of these two digits. But by construction, we have that that's impossible. X sub m, m is equal to a sub m, m plus 1 if a sub m, m is less than or equal to 8, or it's equal to 1 if a, m, m is equal to 9. In both cases, we have this is never going to be equal to a sub m, m. contradiction. And that's Cantor's diagonalization argument in a nutshell. Before we get to the formal proof of Cantor's diagonalization argument, I want us to first consider the decimal expansion 0.9999, and then there's infinitely many 9s in the decimal expansion repeating. If we multiply this by 10, we end up getting 10x is equal to 9.999, and then it just repeats. And now what we are going to do is subtract x from both sides. If we subtract x from both sides, we're going to have on the left-hand side 9x, and on the right-hand side, since we are going to be subtracting the number 0.999, infinitely many 9s repeating, from this here, this is just going to give us back 9, which tells us that x is exactly equal to 1. And so that means that 1 can be written as 0.99999, infinitely many 9s. Another way of seeing this is via geometric series. So we look at the decimal expansion 0.9999, infinitely many 9s repeating. This is the same as the infinite series from 1 to infinity of 9 over 10 to the n. We can apply the geometric series test to compute this, but first we need to make sure that the exponent, when we take the expansion, that we start off at 0 for the expansion. So I'm going to factor off a 1 over 10 out, and so we have 9 over 10, n equals 1 to infinity, 9 over 10, and that leaves us with a 1 over 10 to the n minus 1. In doing this, we can now apply the formula that we learned for the geometric series. And so this gives us an a, which is 9 over 10, over 1 minus the ratio, which is 1 over 10. And we get 9/10 over 9/10, which is equal to 1. And so we see that 0.9999 is in fact equal to 1 by the geometric series test. The reason for this discussion is that in the formal proof, we're going to have to address that we're choosing exactly one representation for the decimal expansion of every real number. Because if we had 0.4999, so, and then infinitely many 9s repeating, this is equal to 0.5 and then 0, 0, zeros. So we're going to make a note in the rigorous proof stating that we are choosing, in the case that we had infinitely many 9s, we're going to be representing that number by rounding the number before all the 9s, and then the rest will be replaced by zeros. And so that's just one aspect for the formal proof that we need to address. So let's go ahead and now prove the theorem. So here is the formal proof of Cantor's diagonalization argument. So we are starting off towards a contradiction, supposing that R is countable. We have from our exercise 813 that the real numbers are equinumerous to the interval 0, 1. And so by assumption, since the real numbers are countable, and we know that 0, 1 is infinite, that tells us that 0, 1 is denumerable. Consequently, since it is denumerable, it is bijective to the positive integers, and so we have that there is a bijective function f going from the positive integers to the interval 0, 1. In particular, f of j is an element of the interval 0, 1 whenever j, of course, is a positive integer. And we write the decimal expansion of f of j as 0.aj, 1, aj, 2, aj, 3, and then we just continue aj, j, so on and so forth, where each of the digits, of course, are between 0 and 9. And so we have that each of these will be, for each m, we have each of the decimals, each of the digits are between 0 and 9. Furthermore, if there is a positive integer k such that a sub j, m is equal to 9 for all m greater than or equal to k, then we replace f of j with the decimal expansion 0.99999. aj comma 1, aj comma 2, but then when we get to aj comma k minus 1, we're going to replace this digit, the a sub j comma k minus 1, and we're going to add 1 to it. And that's the digit we have here, and then the rest are zeros. And so the main thing here is, this is the rigorous and precise way of accounting for the situation of having 0.49999, when in fact it is 5. It is equal to 0.5000. And this way guarantees us that we have exactly one representation for each decimal expansion occurring in the proof. Now we continue as in the scratch work. Now we're going to go ahead and do the following. Let x sub m be equal to a sub m comma m plus 1 if a sub m comma m is less than or equal to 8, and it's going to be equal to 1 if a sub m comma m is equal to 9. So we got our number. In this way we have our x sub m. Next, let x in the interval 0, 1 be given by the decimal expansion where now we have x and now we have x1. Oops, sorry. That should be a 0 point x1, x2, x3, and then we just continue onwards until we got our number x. Since x is in the interval 0, 1 and f is bijective, there exists a positive integer n such that f of n is equal to x. And now we're using the fact that our function f from the positive integers of 0, 1 is onto. Now, by construction, the nth digit of f of n is a sub n comma n, and f of n is equal to x implies that a sub n comma n is equal to x of n. By definition of x of n, we have that x of n does not equal a sub n comma n, which is a contradiction. We conclude that the interval 0, 1 is not denumerable, so it's uncountable, and thus the real numbers are uncountable. And so that finishes the proof of Cantor's diagonalization argument. But as I mentioned, this proof is a far simpler argument than the one that he originally gave in 1874, 18 years prior. Cantor revisited this result upon proving his theorem, since the mechanism behind this proof is the same one that we utilize to prove Cantor's theorem, namely this notion of taking a set x is equal to a and a, such that a is not an f of a. Now, one thing I encourage you to do is to read over the proof in the book for Cantor's theorem, as what they call it, so namely that the power set of the positive integers is uncountable. and then read the proof that the book does for proving that the real numbers are uncountable. Because the proof is different than the one we gave. We gave Cantor's original diagonalization argument. The book does this differently. It uses the fact that the power set of the positive integers is uncountable to prove that the real numbers is uncountable. And so please look over the textbook in 8.2 for those two results over the proofs, as they do give a different perspective on what I did today. And so for our next lesson, we are going to move towards 8.3 and investigate further uncountable sets. And along the way, we will revisit this theorem that Cantor proved, namely that the real numbers are equinumerous to Rn. And so this is the same statement that Cantor wrote to Dedekind saying, I see it, but I don't believe it. And so that's the goal. One of our goals for 8.3 is to use the Cantor-Bernstein theorem to prove that the real numbers are equinumerous to Rn.